Okay, so I'm going to do a couple of examples that would be representative of what you might see, what sort of fluid statics problems you might see. So what we have here is a manometer. Okay, we have um, a pressurized tank, and so the whole thing must be transparent or something because I'm able to measure the height of the of different fluids within this measuring apparatus, this manometer measuring apparatus. So this whole thing consists of three different fluids. We have a fluid of density 1, a fluid of density 2, and a fluid of density 3. You know what I mean? So density 1, must be, so we have water, some sort of oil that's lighter than water, and then mercury, and as the third fluid. And so you have a column of mercury from point 2 here up to point A, and then from point A to point B, the tube is going to be filled with the oil, and then the rest of it on this side and in the tank is all water. All right, and the question is find the pressure in the tank. All right, so what we have here is kind of three separate manometer problems, but run in series. Okay, and so we're going to use that to our advantage. That's how we're going to solve this problem. So we're given P2, which is just standard atmospheric pressure. Okay, so we're just going to go down the chain and find PA, and then the pressure at point A, and then the pressure at point B, and then finally the pressure at point 1. All right, so the pressure at point A is just equal to the pressure at point 2. Because we're going down in depth, point A is below point 2, we have to add the pressures, right? Because the pressure is increasing as we decline, as we go down in depth. So P2 plus the density of the fluid that we're traveling through, which is density rho 3, times G times the depth from 2 to A, which would be H3. All right, so now we know the pressure at point A. Continuing on, we can calculate the pressure at point B is going to be the pressure at point A. In this case, we're going to be going up in elevation, right? So we get a minus sign. The pressure at point B will be less than the pressure at point A. So we got the pressure at point A minus the density of the fluid we're traveling through. In this case, the density of, or density rho 2 times G times the height at which we went up, the change in height, So that would be H2. And then following this on, we got pressure 1, which is the pressure that we're after, is equal to the pressure at point B. Again, we're increasing in elevation or decreasing the depth. So the pressure up here is going to be less than it was at point B. So minus, in this case, we're traveling through a fluid with density rho 1, again times G, and again, this time we're multiplying by the height 1. And so we could just substitute these into each other. So then P1 is equal to PB, which is PA, which is this. I'll tell you what, I'll just go step by step. P1 is PB, so I'll substitute PB in there. So that's the pressure at point B, and then I got to subtract Okay, so I can drop the parentheses now. But so P1, I can rewrite that. So PA is just P2 plus rho 3 GH3, that was PA, minus rho 2 GH2 minus rho 1 GH1. Okay, so I can factor out the G. I substitute my values in. P2 is atmospheric pressure. Okay, so being careful that 101.3 kPa, all of these other units are going to give me pascals, and I have a kPa here, so I got to be careful that my units are correct. So I'm going to divide by 1,000. I'm going to divide this property by 1,000, right? So this is 1 kPa equals 1,000 pascals. All right, so I'm going to convert everything to kPa. And so this comes out to 145.3 kPa. And so this is absolute. This is the absolute pressure, right? I took into account the pressure at point 2. So this is going to be absolute. So what if I wanted the P1 at gauge? The gauge pressure at P1. Well, that would be just equal to this, right? That's going to be equal to P1 absolute minus the atmospheric pressure. But the atmospheric pressure is just P2. So the gauge pressure, I just subtract off P2 and get the gauge pressure, 44 kPa. So if this were a pressurized tank, the forces being exerted, the net force being exerted on the tank itself would be really equivalent to the gauge pressure, right? Because it would have, the atmospheric pressure would be pushing in from the outside. So I have atmospheric pressure operating this direction, and the pressure from in here operating the other direction. And the net is that this wall is feeling a net outward force equivalent to a pressure of 44 kPa. All right. So here's a buoyancy problem. I have there's a spherical shell in the water, right? The shell material has a density of 1,600 kilograms per meter cubed. The density of water is 1,000 kilograms per meter cubed. And the question is, how much of the shell is submerged? So what we have here is an equilibrium issue, right? So what would determine when this thing stops sinking? And the answer to that question is that the buoyancy force, it'll stop sinking when the buoyancy force is equal to the weight, right? If the weight were greater than the buoyancy force, then this thing would be going down. And if the buoyancy force were greater than the weight, it would be going up. So it'll stop when the buoyancy force and the weight are equal. So what is the weight? The weight is going to be equal to the density of the shell times the volume of the shell. Okay? The volume of the shell is going to be equal to the volume of a sphere, a 6 centimeter radius sphere, minus the volume of a 5 centimeter radius sphere. Okay? The volume of a sphere is 4/3 pi r cubed. That's the volume of a sphere. All right. So 6 centimeter is what, 0.06 meters cubed minus 0.05 meters cubed. So in cubic meters, the volume of the shell comes out to be some small value. Okay, so the weight is just equal to the density of the shell, 1600 kilogram per meter cubed, times the volume of the shell, times gravity, times the gravitational constant, that is. And so the weight comes out to be Alright, so then the buoyancy force is equal to the density of the fluid, in this case water, times the volume that's displaced. Times G. So it's the weight of the water that's displaced is the buoyancy force. It's going to be equal to the buoyancy force. Alright, so the volume displaced is going to be some fraction, we'll call it x, of the volume of a sphere with radius 6 centimeters, right? It's the outer surface that's going to be displacing the water. So as this thing gets submerged, the outer surface displaces all the water. There's no water in the interior of the shell, right? Consider it to be like a perfect vacuum in there. So we have an outer shell that's pushing this water aside. So the displaced fluid is just going to be of some fraction x of the total volume of the sphere, and this x is what we're actually trying to find here. And so the volume of the sphere is 4/3 pi r cubed, in this case 0.06 cubed. Okay, and so that's 9.048 times 10 to the negative 4 times x. And this will be meters cubed. All right, so the buoyancy force is equal to the density of water, which is 1,000, the displaced volume times gravity, gravitational acceleration, okay? And so I set these two equal to each other. So I got 5.983 is equal to and I can solve this for x, where x equals 0.67. So about 67% of the sphere, of the shell, is submerged. Okay.